Good day to you. This is Anagalactic bringing you another presentation in geometry specific to heaven. There are earth sciences. We've covered that in previous lectures. Science is huge, but so is the universe, and astronomy calls us. It's a specific calling. It's not an earth science. It turns out that the study of astronomy, although it does require mathematical aptitude, it's not as demanding as for the other sciences. When you get into biology, geology, there's a very long list. Anything to do with engineering, anything to do with technology, well, you definitely need calculus, and you're going to have to spend about $100,000 to waste 16 years of your life so you can become an industrial slave for the very reasonable purpose of attempting to survive just a little bit longer on this goddamned planet. Now, in astronomy, we literally don't know what you're talking about. We've severed our nerves, our hearts are turned off, our souls are complacent. We just turned into Vulcans, kind of like machines, and we don't show any sign of emotion. We don't care about life and death. We don't understand you. Whenever you're talking about anything having to do with earth, politics, religion, philosophy, we just wait. And that's why we're considered antisocial. We're just watching your lips. For when they stop moving, you say Trump, COVID, politics, religion, racism, injustice, your puppy is dying of cancer. And we're not angry. And we're not necessarily annoyed because that's an emotion. No, we just wait until the program is over, till it stops running, which is when you finally give up trying to talk to one of us at all, because we're just staring at you, just not shaking our heads, we're not frowning, we're looking at you, and you know, we're forced to reply, but it's obvious we don't want to. So what do you think? Do you think we should vote for Trump, or should we lynch him? What should we do? And you just don't really respond right away, which is already a bad sign. You know, the person's starting to get angry, morose, starting to feel, terrorized. Why is this person not responding as expected? And we're not and then we become aware of that because we've trained ourselves harshly, just like from the Shaolin Temple or something. And that's our introduction to what it's like to be one of us. I mean, we don't care. Well, you actually have to make sure that you don't care, because you will care, because the world will just keep coming at you. Where's your money? Where is the money? And you're like, well, I was doing science and mathematics in outer space for the past. Did I run out of money again? Well, there goes your heating and your rent. You're out on the street. You're doing astronomy from the bushes. You know, nowhere to poop, no shower, no food, no friends, nobody likes you. They know that you're not listening, you're all thinking of the stars or whatever. Einstein, nobody knows what the hell is become of you. You don't like football because you say it takes you away from your studies. You know, at night you're out with a telescope. What the hell? Are you some kind of public threat? What are you doing? And then you run out of money. No, you can never let that happen. And so the practice of compassion and forgiveness, as taught by the Dalai Lama, Jesus, the prophet, when he wasn't, reminding people that God might be angry, God might actually hold you to account. Well, he's not trying to be negative, as billions of Arabs and Persians know. And they still bow their heads, they're happy. But you're trying to get along in this world, and you're not able to study the truth, and so you never get wisdom, and then you die. And that's just the saddest thing. Well, like I said, you just gotta train yourself not to care. The Ukrainians, let me tell you something about the Ukrainians. They've always been being slaughtered. You can check the history records. Anybody who's living in Ukraine is just, forget it. I went there, I lived there, it's like I wasn't afraid, but it was only like a 5-year period. in between 70 years of communism, and it looks like another 70 years of whatever's next. And the Ukrainians just clubbed down like brute animals. Oh, you're a farmer? Well, whack! You're a farmer, well, take away all their food, their grain, so they can't eat. You know, and if you let it get to you, you lose your mind. I did. I lost my mind. But then I found it again. You can't lose your... If you lost your mind, well, I wouldn't be talking to you if I had just said I didn't tell you nothing but the truth, the whole truth. I didn't tell you the whole truth. That whole truth and nothing but the truth, it's that last one. Oh, no, actually, it's the middle one. The whole truth. Do you swear to tell the truth? Yeah. You got your hand on the Bible, the Dewey, the King James, every version of the Bible. You put your hand on it. You raise your other hand. I probably have it backwards. I've never had to do this, but I've seen it in movies. And you have to swear to tell the truth. Yeah. The whole truth. And now you're like, what? And nothing but the truth. No. What do you mean, no? No, I don't swear to that. I'd be damning my soul to eternal flames of brimstone perdition if I did that. And they have to respect that. Well, take the stand then. I guess, unless the judge were harsh. That's $50. You want to try answering yes now? I'll find you in contempt. They'll drag you away. This case will be closed. You want to play straight now, Sonny? Or he could say, no, his rights. He's an American. He doesn't have to fuck with that kind of shit. Pull that the whole truth. What? He's a scientist, you know. Some guy stands up. I'm his counselor. I'm from the same university as he is. And he's a scientist, and he can't answer that question truthfully. He'd be out of his mind. We'd kill him. We'd drag him away. We'd tar and feather him. We'd throw him upside down into a river till he confessed. He lied. He said he'd tell the whole truth. That's impossible. Kurt Gödel proved that. And, you know, you just don't want any of that. So you retire to the desert. And that's where all astronomers at either that or on top of some bleak, ice-encrusted peak 9 months of the year. We come down for Grange. We just, get more toilet paper, renew our broadband connection. And then back up Everest and look at the stars while we're freezing to death through our telescope because our soul is migrated already. We're trying to see where it went. It's among the stars by now. It's way out there. I can hardly wait to die so I can catch up with it. And meanwhile, your buddies from the football league and, the beer drinking squad, the ones who just try to, fuck with you every way they can because they never grew up. They don't listen to you, and now they don't know why you're not there being victimized by them as always. You're off studying books, or Roger Penrose, Albert Einstein, God knows what you're doing. You're all holed up, you don't even come out for the virus, you just stay inside. You find out last, if you're me, about the COVID. I learned about it 3 months after the rest of the world knew. I hadn't really noticed. I thought, well, people are wearing masks. That's a good idea. The Japanese do that. And I found out there's a frickin' virus. It's either from a monkey or a bat. It's either Mongolia or Africa. I honestly don't care because it's a virus. It doesn't, tell you where it's from. It just comes and gets you. And if I get it, I'm dead. But I find out there's this COVID virus, and I'm like, everyone's like, oh, you're just finding out. Wow, that's tragic. Because, we're all having to lock ourselves indoors. It's not going to go away for 2 years. Everyone's going to have to stay inside. It's restructuring the whole infrastructure of communication and life on Earth. Technology is disrupted. Shit's piling up on the docks. Nobody can relate. The children are kind of slowly losing their minds. They're all cooped up. They can't. And I'm like, fucking didn't affect me. I didn't even notice. I'm like, good. And that's, again, now every head at the dinner table turns and looks at you. they're not sure they heard right. Now nobody's talking, and then your interlocutor just, did you say that you think the COVID virus lockdown is good? Is that what you said? And then, you're trained. You've trained yourself. This is a dangerous situation. And you just immediately stuff your mouth with some turkey, gravy, and start talking with gravy coming down your chin. Lean forward and say, I've always wanted to address this question to the family. And since it's Thanksgiving and you all need to know, the COVID virus is really, really good for science and particularly for myself. And I don't want you all dead, but obviously that really wouldn't affect my work. And then go back to stuff it, you've been chewing the whole time. And now everybody is like unknown what to do now. Unknown situation has arisen here. One of our own genetic kind, he's part of the family, not for long. He likes the COVID virus. Well, what about the war in Ukraine? And I'm like, what? Last I heard it was Yugoslavia. It spread to Ukraine. They're like, where have you been? You don't listen to my lectures? They're looking at each other. What? I've been in heaven, you baboons. I'll bet you all believe in natural selection, right? You're eating monkey meat so you can turn into monkeys even more. This isn't turkey. This is monkey. And now they're like, fuck, he's ruining the holiday. And that's the introduction to our lecture today on Boscovich. Only 12 minutes of ranting this time. You see, I've brightened up my act. I've learned 3 different ways to not tie a tie right. I know the 4-square knot, the Windsor knot. I can't do any of them. I do it, that one. Oh, goody. Every time you've seen me before, I've been wearing a different knot that looked normal. This is the one I learned when I was 10 because I can't remember the other 2. And it looks the same to me. I don't know why men wear ties. Only a Homo sapiens would tie a noose around his neck. Someone could just grab it and that's the end of the fight. He just pulls it and holds on, closes with you, just keeps yanking on it until you're dead. Or you tap out, he just waits till you turn blue. Like your tie. So, Roger Boscovich over here. We're going to switch over here since I'm all set. You see I can highlight stuff. I noticed you can't see the mouse. My technological capacities don't have great reach right now. That will change. I will be getting software. It costs like $100. So I'm delaying as always. And here's where we're going to begin. Let me just center this so you can see it all. I think you can see that. Yeah, let's get the date in there. See if we can scroll this a little. It's not moving. Oh, it's at the top. All right, so there it is. What we have is the continuity principle, which is attributed to Leibniz. Now, this is the subject of today's lecture. The continuity principle attributed to Leibniz has a couple of confusing aspects. This confused me, so I'm passing it along to you. Since it does say Leibniz, this is specific. This is Leibniz's idea of continuity. There's more than one idea, but they are convergent. What is the basic premise behind wanting a law or principle of continuity? Continuity of what? Very good question. That's actually the problem, is continuity of what? The real question, which gets down to metaphysics, believe it or not, yeah, it's just not going away. You've heard of the continuum. Do you know what is being talked about whenever you hear the word continuum, or you have heard it in the past? What does it mean for something to be continuous? Well, it depends on the thing. That is the problem. It really is. It goes right down to the quantum mechanical paradox. And it has to do with a lot of different subjects. This is extremely basic, a very, very basic, not exactly mathematical, not exactly geometric, not exactly anything, because actually what you're talking about is the definition of being exact. If time were continuous, that's one domain, how would you know it? Let me ask you another question before trying to answer that in any way. What about space? Is space continuous? Well, you may have a pat answer. You may think, well, oh, come on. But actually, we're still listening because we already know. We're not sure what you're going to say. Oh, yeah, okay, it's obvious to you then that space is what? Continuous or discontinuous? It's continuous. That's Newton. What about time? Continuous. That's Newton again. Along comes Albert Einstein. Now, in between Newton and Einstein are quite a few scientists who talked about this. Did anybody talk about it before Leibniz? Who was the earliest? Was Newton earlier or was Leibniz earlier in their notion of continuity of either space or time? There is a third one, and there's actually a fourth one, and there may be others. But let's count them. These are called domains, and the domain refers, in this case, the most abstract domain, the domain of inquiry. And so what is the thesis? What is the topic of discussion? Continuity. Okay, if you just start out in your lecture saying it's the law of continuity, whether of Leibniz over here or someone else, such as Kepler, let's start with Kepler. You can see by the date, he's a century earlier. These are ballpark figures. Leibniz was 1700, about. Kepler was about 1600. What was his law of continuity? It's different for every man. You have to inquire what he means by that. It's by no means a single definition or a single answer. The four domains. First of all, you could have class domains. Physical continuity. Are you talking about reality? Well, that raises an interesting topic as well. Oh, but in any case, reality or mathematical would be the other choice. Is there such a thing as mathematical continuity? That has been the subject of millions upon millions of books and articles. Millions of them, for centuries, have dealt with mathematical continuity. We're not going there at this moment. But of course it has to have something to do with mathematics. The way most of these men think, certainly in the present age, it must have direct bearing on mathematics. Well, why not just deal with it mathematically and forget about reality? Just check to see if the numbers are continuous in whatever situation that you may need them to be continuous or you may not want them to be continuous, and then just adapt. So it may not have a yes-no answer. It may depend partially on you, that is your needs. If you're doing a measurement, that is actually a quantum mechanical paradox called the measurement problem. From now until the solstice, I will be rehearsing the discoveries that I made in 2022 to answer these paradoxes using a certain geometry, which is, you'll see. And that is what we're doing today, is beginning. We're beginning with R J Boscovich. Where does he fit into this picture? Let's go on a little bit, but let me complete this page. We do have Leibniz's idea of continuity, a heuristic principle based on earlier work by Kusa and Kepler, so it is the principle, and here's our introduction. Whatever succeeds for the finite also succeeds for the infinite. This may remind you of the calculus, which is defined in two ways, whether you're Newtonian or Newtonian or Leibnizian, I guess you would say. They had two different definitions, or two different approaches. Although you're required to address both approaches, one is called the limit, and that's more or less Leibniz, I believe. Let me scratch that. We'll come back to that. We're actually getting to that. But when you learn the calculus, you learn both the limit. That's actually a theory of how to define it. And the other one is the infinitesimal. The infinitesimal, I will show you which one of those is correct. Either the limit definition of calculus or the infinitesimal. They converge on the same thing. And what that is continuity. And continuity has been abrogated. As if the Pope came out on the balcony in some millennium and just held up his hands in his white robe, the mitre, everything, millions in the street listening, he's coming out to tell us something. Quantum. The quantum, you know what the definition of the quantum is? It's the answer to continuity, and the answer is no. And the answer for any continuity. Time, space, mathematical, although there's a fudge, we'll get there. What we do here is geometry. That's why I've been studiously avoiding the word geometry. Geometry is how you get understanding, but if you're using numbers, you're not using understanding. You're using numbers. If you want understanding, you're using geometry. They're very closely related, but that has been forgotten. So, we're remembering it. And these guys, Kepler, Leibniz, Newton, and Boscovich, and Nicholas of Cusa, apparently, and Archimedes, also did the calculus. All these guys did the calculus because they're trying to figure out the law of continuity. The one that we want to concentrate on for the duration is going to be, you can see words down here like arithmetic, transfer principle, infinitesimal calculus, the mathematical implementation, hyperreal numbers. Oh my God, what is that? Don't worry about it. I did. I'll tell you what those are. They're actually predictable. Once you know what hyperreal numbers, you go, oh, well, it was just eventually somebody was going to do that. When you're trying to get at continuity, you're going to do every fucking thing you can. And it fractalizes. And it turns into a paradox, which has been given a name, although it's a system of paradoxes, called the quantum mechanical paradox complex. I've counted well over a half a dozen separate paradoxes that are associated with quantum mechanics. Let's start out there because that's where we're going to be going in future lectures. What is quantum mechanics? It is basically the study of the principle of continuity, which is a heuristic principle. What does that mean? What is heuristic? We'll come back to that. Rather than delving into sidelines and getting definitions, which is a part of science and quite critical, we're going to have an overview of this now. So let's go on. Kepler used a method in order to calculate the area of a circle. Well, you and I are vastly interested in that. That is geometry. That's geometry. That's what we want. Because we are looking for understanding. We're not interested in having a dictionary of all the problems, paradoxes, conundrums, dead ends, fake mathematics, horrendous division by zero problems. Everything is irrational. Nobody knows what to do to get further. We don't like that. We're not entertained by that. That doesn't impress us, except in one direction. Get the fucking answer. What the hell is holding things up? Well, I'm going to show you what's holding things up. It's the law of continuity. So, you can look at this later, because you can take a screenshot and read this. But I promised to mention something about hyperreal numbers. Well, here's a function down here. Oops, let's just leave that where it is. I just highlighted it. You see how I do that? Highlight, unhighlight, highlight. There you go. But it doesn't show the mouse. I wish it did. Let's keep moving because we're already at 25 minutes. I'll be covering this in great detail in upcoming lectures. But I want you to know what we're going to be doing. This is extremely exciting stuff. You're going to be vastly impressed with every step of this. But in science, you really have to bear down. And I take the gentle approach. I don't want to wear you out with just the reference here and check this and we're learning this math first and you got to see another video and I'll never finish my sentence. Yeah, and you're waiting. I'm watching this for a reason, but I forgot why. We don't want that. Why can't we divide by 0 again? All right. And here's something I just needed to get these letters. Let me just show you something here. There, we'll get that. Look at that. You reckon these are kinds of number systems? Well, they're all linear. All of these are linear, except for this one. That's complex numbers. But as I've pointed out in prior lectures, sorry to put it that way, but I'll just sum it up here because science is nothing if not summation. You don't have to watch previous lectures. I'll sum it up in 20 seconds, what it took me a whole lecture before. Well, part of it. But the complex numbers are linearizable using conjugate algebra. And so there are linear numbers, but only because of a specific algebra that allows I to be converted back into real. Well, you have to do that because the computers do not know what I is, okay? They only know what linear numbers are, and barely that. But complex numbers, no. But I myself have programmed in the conjugate. There's a few functions you have to write. I am a programmer, so I make it sound easy. You may be, what? He must be a genius. We're all geniuses. You don't ever think that. Okay, don't want to get off too far. The complex numbers have two components. That's very good. The number system that I discovered for the second geometry is a two-component number system. But you can't use imaginary in geometry. You can't. You can mathematically, and it works marvelously if you love irrationality, because that's all it is. You're using linear numbers for circular and spherical, which is to say curved space. That includes parabolas, hyperbolas, paraboloids and hyperboloids, and ellipses and ellipsoids, and that's about the whole list. But what they are a different kind of line, which is most of the lines in the universe are not straight. That is well known, so you can just, if that's news to you, like, oh my God, I'm converted to a new religion, well, you're just catching up with the rest of us. Albert broke the news to us on this. So the complex numbers are the only ones in this that might be considered anything other than just standard linear numbers. But those are the symbols that I needed to know because I have my own. Let me show you some of my new symbols so you can get a good look at these. Look at that, Charlie. See those symbols? Each one of those has a meaning. This is Unicode over here. Never mind. And going on to get past my notes, Theoria Philosophiae Naturalis. Now, I don't speak Latin, so this thing at the end here, you can see it. I and then an AE ligature. You may know that my ligature, I've adopted the capital AE for my company logo. But it is an old Latin letter, and it appears here. It's a plural form, I believe. Plural neuter. Well, this is just neuter. Theory of natural philosophy. Well, that's what they called it. Natural philosophy. You know what we call it? science. You see a split there over the past, let's see, 300 years. Getting on, it's 2.5 centuries earlier is what we're talking about here. It's a book by this man, RJB, Roger Josip Boscovich. Here's the pronunciation. Let me just accelerate this up to visual mode. Roger Josip Boscovich. He's Croatian, Hrvatska. It's on the Adriatic. We covered that in the last lecture. Let's go on. This is the Venetian edition. It was published more than once, which is really saying something. Back in 1758, and then 1763 is when it was actually published, but he began it in 1758. These are ballpark figures. You see, they're not really ballpark. It's more like which row are you sitting in. And then we get down here. These are his words. In the first 6 articles, I state the time at which I evolved my theory of what, and then this was a typographic error in the text. Let me erase that. What led me to it, and where I have discussed it hitherto in essays already published. In other words, Boscovich had been working on this for a long time. And here's what I want you to see right at the end. I'm going to read this whole thing beginning right here. In the first 6 articles, I state the time at which I evolved my theory and what led me to it. So the history of his theory. What is this theory? I've also discussed it in essays already published. Also, what it has in common with the theories of Leibniz and Newton. He was their contemporary, and he was the most famous scientist in Europe. Boscovich was. Certainly in France and Italy, also in Germany, and he went to England, and that's a hilarious story. He actually went to England. So did Leibniz. And both of them were very nearby where the king was, and we all hear about Newton, Newton, Newton. For every 1,000 things you hear about Newton, you hear about maybe 10 about Leibniz, and none about Boscovich. Reverse that. Boscovich is at the top. He learned calculus from both Newton and Leibniz. And then, here's his theory. What my theory has in common with the theories of Leibniz and Newton, in what it differs from either of these, and here's the good part, and this guy is not kidding around, he's a priest. He is. And he says, and in what? Wherein it is really superior to them both. This is translated from Latin, by the way. I'd like to know what it says, really superior in Latin. Maybe we'll cover that. I may leave a note. We're going to be spending a few lectures on Roger Boscovich because it's cutting edge. It's cutting edge. And it's coming back. And I'm going to spearhead its attempt to come back. Boscovich's curve. The theory that he's talking about is a simple curve. But it's not simple in the elementary sense of a single curve. It's actually a multiple curve. And it's in its simplest form, it's 2 curves. And it describes the relationship between time and space. And Boscovich did not actually say that. But I recognize it. And so will you. He described the electron orbital shell well over a century before Bohr discovered it or Rutherford surmised it. The atomic structure, which is shells, spherical, parallel spherical shells. You know that from quantum mechanics. This guy discovered the geometry of it. In addition, I have published elsewhere about equilibrium, a major topic on my agenda. This guy has it. He has it. And the center of oscillation. He's talking about something that I discovered. He has the term for it, I have the discovery that corresponds with this. It's geometric. And it is for Roger as well. This is extraordinary stuff for me to have found this for corroboration of my own work. Having found out that these matters followed quite easily from a single theorem, that's his curve, of the most simple and elegant kind, you will see that. I will show that to you more than once. We're going to be talking about this curve. And that's his theorem. He's talking about his theorem of the Boscovich curve, and you can look that up in Wikipedia. The Boscovich curve. If it doesn't blow your socks off, it's because you're not a scientist. So, of our caliber, this is the highest level of science. Read my lips. This is science. You're not going to find this anywhere else today. What I'm doing is the beginning of the resuscitation of the comatose body of physics. It's been dead for 70 years. With brief flashes, science progresses in spite of all obstacles. The obstacles we're facing right now cannot be solved any longer, and we know it. But they have to be. Well, let's see how we can do it. Nobody else can. Boscovich can, though, with my help. These are still Roger's words. It's from 1760, yes. From this until Article 2, I explain the theory itself. And here it comes, it's in yellow. The word problem form. Once you see the diagram and I explain it geometrically and mathematically, don't forget he knew calculus. He was the foremost practitioner of calculus that ever lived until Albert Einstein himself. But not even Albert knew it as deeply as Boscovich. And that is starting to be re-recognized. And you're going to see an explosion if you're lucky, because it has to be suppressed. This has to be suppressed. What I am telling you now is deadly serious knowledge that cannot be released to the public due to irrational mistrust. We'll come to that. Here it is. I will explain the theory itself, that matter is unchangeable and consists of points that are perfectly simple, indivisible, and of no extent, and separated from each other, that each of these points has a property of inertia, attractive force, depending on the distance in such a way that if the distance is given, both the magnitude and direction of this force are given. But if the distance is altered, so also is the force altered. That's it. If the distance is diminished indefinitely, this is one of two examples, the force is repulsive. And in fact, also increases indefinitely. That's not infinitely. Whilst if the distance is increased, the force will be diminished. Sounds like gravity. It will vanish, be changed to an attractive force. Yeah. That first of all increases, then decreases, then vanishes, is again turned into a repulsive force. This is a wavy curve that looks like a Fourier diminutizing curve. It goes from a big wave to a littler wave, big wave, then littler wave, then littler, then littler. I'm going to show you where that ends. And that will be the locus of continuity and the answer to the problem of is space continuous or not, and if time is continuous or not. And I'm not going to give it away, but I think you're starting to see something, right? So, don't worry about the rest of this, but I did want you to see this down here at the end, the very bottom of the page, abscissae and ordinates. If you're anything like me, that just sounds like Greek. It's worse. It's Latin. Abscissi are X. Abscissi is plural of abscissa. It means X. Abscissa means X. That's what it means. Why not just say X? It's Latin, okay? This is how they talked back then. They didn't say X and Y in this kind of a paragraph. They said abscissi, which you might think is pretty well named. You sound like a sissy. And as for ordinates, I would have thought those were the X coordinates. Wrong. I'm dyslexic that way. But I have it now. And I've also associated abscissi, which is X. Ordinates are Y. They're the Y coordinates. They're the... Well, think of... Well, you have to make a mnemonic. Well, there's also cosine and sine. Which one is X? It's cosine. We give them backwards, don't we? Abscissi and ordinates. Well, actually, that's in the right order. I told you I'm not... Oh, by the way, that was translated as an S there. Let's make that an A. So now it's abscissi. And that the X, the cosine, is what you would think of that as. That's X. Sine is Y. Cosine is X. Abscissi are X, and ordinates are Y. Okay? So what do they represent? X is... The horizontal coordinate is distance. That's for the curve. We're going to show it to you in a moment. And the distance from the y-axis is actually above or below, depending on repulsive or attractive force. This is a force law. And I just got finished in my previous lecture series proving that if we want to understand space-time, we're going to have to understand it the way nature actually expresses it, which is in energy units. Max Planck discovered that. In other words, that's not space. It's not space, which means that science literally can't handle it. If it's not linear spatial separation, we literally know not the fuck what to do. And that is painfully obvious now. It's not just sine cosine. That's the sign of a disease. It's the calculus. And I've solved it, so don't worry. We're going to show you some more here as we finish this off in 45 minutes. 3 minutes to go. There will be another lecture. Well, there are going to be lectures running until the summer solstice, if I live that long. You always have to add that if you want to. This is amazing stuff here. You see I have highlighted. This is Boscovich's term, hyperbola of the third degree. Now, what in the world does that mean? I tried to find out. If you do find out, I would very much appreciate, to the point of even rewarding you, leave a comment. I know what he meant by that. I was able to find out, and I'll have links for how you can find out, because he's attributing that to Newton. Well, were you taught Newtonian gravitation as a hyperbola of the third degree? It took me a little while to even find out what that means. It does have a meaning, but it's not really in Newton's work. Principia Mathematica, or whatever it's called. Latin again, of course. Latin is a dead language, dead as can be. First it killed the Romans, and now it's killing me. My mother learned that because she learned not calculus. Well, thank God. Nobody should learn calculus unless you learn it from me. I'll teach you calculus. But not with a 20,000 page book in the tiniest print with no answers and no way to understand it. Just millions and millions of pages, endless pages. You'll never understand calculus unless you understand it geometrically. I will be showing you exactly that. And you'll never need it again except to know the simple derivative, not partial derivatives, not second order derivatives, never an integral. You'll only need to know the simplest form of the derivative. And why? That's in the previous lectures. Let's continue. Just to complete the sentence, so you'll be able to get the linear numbers back out of the spherical number system to compute them. You have to come back to your nest. You can't escape linear numbers, which is why my discovery of the spherical number system is miraculous, and it explains why nobody ever saw it. Because if they're spherical numbers, well, they're not linear, are they? Actually, they are. So we'll get to that. And here it is again. I have this more than once. The hyperbola of the third degree. Omar Khayyam got the solution to a third degree equation, and that was the beginning of my journey. Newton's hyperbola is by Jiří Stavek. I believe that's Hungarian. It might be Czechoslovakian. It's somewhere in Central Europe. But this has to do with Isaac Newton's focus of radii of curvature of both the ellipse and the hyperbola and the parabola. The evolute of these conic sections, and centripetal force means gravity. So what Newton, well actually what Boscovich meant in referring to Newton's system of gravity based on third order hyperbolic geometry, right up here I show how it differs from Newton's hyperbola of the third degree. You don't need to know that. That's the answer. So, here we get some more from Stavek, elastic spacetime. He's talking about Boscovich, believe it or not. And there's more stuff in here. You can study any of this. You can study forever, but we actually are after answers. So there's a little bit about how Hamilton contributed to this. Another reference to Kepler. An interesting term, hodograph. You don't need to know that. Pedal curve. You don't need to know that. It's all fascinating. But what we want is Boscovich's interpretation of gravity, don't we? It's superior to Newton's. Albert Einstein replaced the classical model with elastic spacetime. That is incorrect. It's technically correct in a very limited sense. And the problem is not elastic. By the way, elastic means it curves. Elastic means it curves. Trust me on this. We'll be back with that. But spacetime. Spacetime is a valid concept. What is not valid is elastic spacetime. Now, Einstein proved that there is elasticity, that is curvature, in spacetime. But the problem that nobody has been able to realize they're perpetrating is they're saying that spacetime, as a construct, it is actually a geometric space, and believe it or not, it is hyperbolic. But when you say that it curves, you're saying that both space and time curve together. That is Einstein's formulation of spacetime. Both of them curve. That's incorrect. Only one of those two can curve. And exactly one. The other one will be linear with respect to the one that curves. So if space curves, which is the formulation that is most correct in my opinion, because you could say it either way, time could curve, that's kind of a mind bender. Well, space can curve, that's less of a mind bender. So we choose space for the curvature component. That means that time is linear. That's actually the best match on our experience, is that to the degree that time is linear, space is curved. That's correct. But it's not space-time that's curved. It's either space or time. In one of the two, it's either space-time or time-space. They are different. It depends on which one. We'll get back to that. That's actually a bit of a complexity. Let me finish this sentence, though, otherwise this would be frustrating. Newton thought of space as being linear and time as being linear. Albert said, if you make them both curved, you get space-time. That is incorrect for both space-time and time-space, because it's a 3-1 or 1-3 split. You shouldn't do either one of those. It's a 2-2 split. And I'll show that to you. That really is the basis of my discovery as it's applied to Einstein's field equation. His 3-1 split for 3 lines and then an imaginary line, obviously incorrect. Well, what's the truth? Instead of 3-1, you do this and make it 2-2. But there's no mathematics or algebra for that. Because there's no geometry for it. Yes, there is. I discovered it last year. So here is some more. You can read this later. And this is basically where it ends. There's some more. I was looking... Never mind that. All right. So that's the end. And I hope you enjoyed this. That's 51 minutes. That's enough. I try to hold in at 40, but my tendency is to go an hour. To compromise at 51 minutes is good. I hope I don't wear you out. I hope I don't go too fast or too slow. But I hope you realize that we're homing in on the Boscovich Curve, which describes atomic space before the atom was discovered. We'll be right back. This is Anagalactic on the 5th day of February, beginning our new series, which I am going to be calling basically the Boscovich series. The most amazing polymath who's ever lived, and the last. He's been called the last of the polymaths. He was a Catholic priest, a very good man, as far as I can tell. Of course, it helps when you're a scientist. You're not usually called off to war or butchery or something for politics. No, you're just doing your stuff for the king, the pope, whoever. But you're righteous. He was, in my opinion. Excellent writer. I think he's the greatest scientist who ever lived. I just found this out within the past 6 months, though. But I love this guy because he corroborates my discoveries, which are definitely correct. We'll be back. Anagalactic. Stay tuned. You don't want to miss these upcoming lectures.